I'm going to start this video by talking about the first law of thermodynamics. Now, the first law of thermo effectively states that the energy in the universe remains constant. So the universe itself as a whole can never gain or lose energy. So what does this mean? Well, there's a few relationships we can derive from this. So that means that we have the delta E. So delta E is just the change in energy of the system has to be equal to the change in energy of the surroundings. What are the system and the surroundings? Well, effectively, the system is whatever we're talking about for that problem. So generally speaking, it would be whatever chemical reaction we're referring to at the time. And the surroundings are everything else. Of course, it doesn't have to be a chemical reaction. If we put, two things in, so if we're talking about a metal block touching water, like we did in the last problem, we could think of the block as the system, and the water as the surroundings, or vice versa. So basically, the system is what we're interested in, the surroundings are everything else. So the change in energy of one has to be equal to the change in energy of the other. Well, equal in magnitude, opposite in sign, which you don't have to worry about for right now. But that just means that if the system is giving off energy, that means that the surroundings has to gain an equal amount of that energy, so that the total energy of the universe can remain constant. Now, also, the change in energy is going to be equal to Q plus W. So Q, as we talked about last video, is the heat, and W is the work. And there's another term called the internal energy, which is represented by delta U. But you can effectively think as delta U and delta E as being the same thing. So delta U, which is talking about basically the internal energy of the system itself, equals Q plus W. So the change in energy of the system is going to be equal to the heat of the system plus the work done on the system. So for heat, now if we're trying to tell if the change in energy is positive or negative, for heat, if a system absorbs heat, so let's say if heat is absorbed, so that means that Q is going to be a positive number, so that it's positive, and that's called an endothermic process. So if heat is absorbed, Q is a positive value, and it's an endothermic process. If heat is released, that is now a negative value for Q. And of course, if Q is negative, if there is no work done, which I'll talk about that a little later, that means that the change in energy would also be negative. And if that's the case, that is referred to as an exothermic process. For work, if work is done by the system. So that means that if the system does work on the surroundings, that is a negative value. And it might seem a little counterintuitive that if the system is doing work, its value for work is negative. But remember, we're talking about the internal energy, right? And think about it this way: if you are pushing a block, you are the system doing work on the block. And if you're pushing a block, that's going to take energy. So you have to use up that energy, which means that you have less energy after you've used it. So your total energy has to go down. And so the opposite of that, if work is done on the system, then your value for W is positive. So if you're given a value for heat and for work, you can just add those together, and that'll give you the total energy change of the system. Another term that you'll hear quite a bit is called enthalpy. So enthalpy is a very important term. It's represented by delta H. And it's a measure of the heat transfer in a chemical reaction. Now, if you recall last video, I said that in order for work to have been done, something needs to move a certain distance, right? Which means that, so if we have a chemical reaction, the only way that work could be done is if the volume changes. Basically, it has to expand or contract the volume that the reaction is in. If that does not happen, if the volume remains constant, then enthalpy is effectively equal to Q, delta H and Q. And so even though delta H and Q are not technically the same thing, for the sake of this class, you can consider them the same thing. So delta H will equal Q. Now, enthalpy is measured by an instrument known as a calorimeter. So the calorimeter is just the instrument that a chemical reaction can be done in, or if you've ever wondered how they can figure out how many calories are in food, because remember, calorie is just a unit of energy, right? They can use calorimeters for that, hence where the name calorimeter comes from. Calories. It's a meter, basically, that measures the calories, measures the energy. So they can measure that in items as well. They can actually burn up the item, and the calorimeter, when it burns it entirely, it can actually measure the temperature change, and using the Q equals mc delta T equation that I talked about last video, they can figure out how much energy that item had in the first place. And another version of this is something called a bomb calorimeter. Sometimes it'll be referred to as just a bomb. So if you ever hear anything done in a bomb or in a bomb calorimeter, what a bomb calorimeter is it's just a calorimeter that specifically has a constant volume. Right? So it's designed so that the volume cannot escape, or cannot change. And basically what that's really effective for is when things are burned up, they often turn into gases. And gases will change the volume of something if they can. So bomb calorimeters are very useful when you're dealing with gases, so that you know you have a constant volume. And if you have a constant volume, then once again, delta H is equal to Q. Then just a few more relationships that I want to talk about here. So the enthalpy of a reaction is going to be equal to the sum. So this right here means sum of the number of moles times the standard enthalpy of formation. And in a bit I'll talk about what standard enthalpy of formation is of all the products, minus the sum of the moles times the standard enthalpy of formation of all the reactants. So for instance, let's say I'm just going to use A, B, C, and D as generic elements. So let's say we have a reaction and it's 2A plus 3B going to 2C plus D. So these are your products. So if you're trying to figure out the enthalpy of the reaction, you would have to, so remember, we want the sum of all of these. So you'd have to do the moles of C, which is 2, times the standard enthalpy of formation for compound C, whatever that is, plus, so the coefficient for D is just 1, so it would be just 1 times the standard enthalpy of formation for compound D. And you'd have to add those together, so that's what I mean by the sum of the moles times the standard enthalpies of formations, and you subtract the entire thing for the reactants as well. So now we have to do 2 for A. I'm doing the moles, 2 times the standard enthalpy of formation of A, plus 3 times, running a little low on room here, standard enthalpy of formation of B. And again, I'm going to add those together, A and B, because of the reactants. And that's what you would have for, and that's how you can calculate the enthalpy of the entire reaction. So just one last concept I want to talk about in this video is the enthalpy of formation. So the standard enthalpy of formation it is the energy to produce 1 mole of product from its components in their standard states. So what does that mean? Well, if I were to ask you to write a formation reaction, which I'll give you a hint, there's a good chance that I may ask something like that on a quiz or an exam. So, to write a formation reaction, let's say I want the formation reaction of glucose, C6H12O6. Whatever you are trying to form, you need 1 mole and only 1 mole of that in your products. Right? So that's it for our entire product side. It's just 1 mole of whatever we're trying to form. Now, we need to break it up into its individual elements and write them in their standard state. So standard carbon is just monatomic solid carbon. Remember, hydrogen and oxygen are both amongst your diatomics, which means that their standard state is in their gaseous form, because all of the diatomics are gases, except for bromine. And so it's H2 gas and O2 gas. So we need to say we've got carbon plus H2 gas plus, kind of ran out of room a little bit there, so O2 gas. And now we just have to put coefficients to balance. We need 6 carbons. We need 12 hydrogens, but it's H2, so we need 6 to balance. So 6 times 2 is 12. And we need 6 oxygens, so we need a 3 here. And that's it. And that's how you would write a formation reaction.